complex numbers hold a geometric significance?
Complex numbers consist of two distinct parts, a real part and an imaginary part. This is why we can think of complex numbers as two-dimensional numbers, because the only way to plot these numbers is using some sort of Cartesian plane.
But can we go beyond 2 dimensions? Can we create higher dimensional numbers? We can create a new class of 4-dimensional numbers, namely quaternions. As the name suggests, they consist of 4 distinct parts, 1 real part and 3 imaginary parts.
The only way to plot quaternions is using a 4-dimensional coordinate system which has 1 real axis and 3 imaginary axes. Due to this, we require 3 unit quaternions, I, J and K, whose multiples label the 3 imaginary axes. I, J and K are known as the basic quaternions and are defined to be the square roots of -1. Hence, a quaternion is a number in the form a plus bi plus cj plus dk, where a, b, c and d are real numbers and dictate how much of each element makes up a quaternion. But what is the product of two quaternions? Just like we did for complex numbers, we can expand the product of two quaternions using a distributive property. During this process, the product of the basic quaternions amongst themselves will come in handy. Like the definition I squared equals -1 helped us in complex multiplication.
How do we derive these basic quaternion rules?
Thinking of unit quaternions with no real part allows us to think of them as vectors in a 3-dimensional space. For example, thinking of I and j as vectors in 3D allows you to compute that cross product, which turns out to be k. The non-commutative nature of the quaternion multiplication can be understood by the anti-commutative nature of the cross product.